All right, guys, we're going to run through a couple of the examples. Here's problem number 18 from section 4.4. It says the base of a rectangle lies on the x-axis, while the upper two vertices lie on the parabola y equals 10 minus x squared. So that's this instance here. Now this is all the infinitely many different rectangles that you could uh, view with this problem. Okay, and we're going to go through this whole problem a couple different ways here. Okay, including using your calculator. All right, because this will reference some future problems you have to look at. Okay, so then it goes on to say, okay, suppose that the coordinates of the upper right vertex of the rectangle are xy. That's this point here at C is xy. Okay, and you are asked to express the area of the rectangle as a function of x. So again, here's what I'm doing. I'm looking at this point E as xy. Now that point here is subject to change. Its coordinates are right here, but those are always changing, as you can see. So since they're always changing, I'm going to state that this is the coordinates of this point are x comma y. But the y value is simply the function value, which is always 10 minus x squared. Okay, so bear that in mind because the point on this curve is always xy, but y is always 10 minus x squared. So the point could just as easily be labeled x comma 10 minus x squared. Um, so invariably, they're asking us to find the area as a function of x, okay? So at some point, we're going to want to optimize that area. I'm going to show you how to do that because you should know how to do that for future reference anyway. So since this point is xy, that means that the distance FD, which I have here, is the same as the x value, okay? And the distance ED is the same as the y value, but it's not x times y, which gives you this area of this rectangle. Okay, it is not x times y because clearly you can see if I'm taking the product of 2.7 times 2.7, it is not going to give me 14.58. In fact, it'll only give me half of that because the dimensions of the rectangle are 2x. That's this whole length AD by FD. So the dimensions of the rectangle are, okay, 2 times FD times ED, which is 2x times y, which is 2x times the quantity of 10 minus x squared. So um, we're going to look at that now and develop that equation, then turn it to the... Okay, we're back. So what we've designated here, just let me mark this off and then we'll turn our attention to the calculator to illustrate a few things. So we've determined that this length is 2x, okay, and that this height is y, and that the area of the rectangle here is 2x times y. But we're asked for an area function, so a as a function of x. So then what we get is 2x, and we said y is right here. It's 10 minus x squared. So it's simply 10 minus x squared, okay? And so that's the function, area is a function of x. There it is right there. So it's negative 2x cubed plus 20x. You should agree to that. That's when distributed. Negative 2x cubed plus 20x. Now, what are the range of values for x? Well, if we went back to the sketchpad example here, we could see here's our value of x, FD, okay? If the point E was all the way up here, then my FD is rapidly approaching 0. And it couldn't be 0 because then I wouldn't have any area, okay? As you can see, my area is just about disappearing. At the other extreme, the x value could be all the way down here to where it touches the axes, okay? In which case, the x is, of course, the intercept value, okay? That's the intercept value. So there are limitations on what x can be. not so much as from the function we're going to see, but because of the situation we're trying to map, which would limit this x to the square root of 10, which is the x, which is the x-intercept there. So when I come back and I look at this situation here, I'm going to state that the areas of value, which is what we're going to call the domain, the x value needs to be between here and the x-intercept. So that x is between 0 and root 10, okay? Root 10, so somewhere a little over 3, I guess we'll say, okay? So now, this is, we're gonna hold it here, and we're going to go, and because this is not quadratic, we do not have a way of analytically finding what the value of x is for which that is maximized. But we can turn to our calculator, and that's what we're going to do now. So we're going to pull up the calculator. I'm going to feed this function in, okay? I'm going to feed that function in, and that function is going to be, okay, um, the as we see here, okay, which is negative 2x cubed and plus 20x, and we're going to take a look at that. But now you got to know where you're looking, because if you just look at that in your standard window, you may or may not see what you need to see. Okay, so we're going to look at that now. Okay, we're going to look at that. I'm just going to clear out the rest of these things. I want to make sure they're not going to show up. Okay, so there's our function we're going to look at. Now, if you look at that in the standard window, you're probably not going to find anything. So let me just make sure we're set to the standard window. Okay, and if we look at that in the standard window, you may or may not find anything. So you're not finding a value for which this is optimized. This is a graph. This is what that graph looks like, okay? It's a standard cubic graph, okay? So let me go back and take a look at it again. And um, this is going all the way down to some point. Oh, we back up, okay. So this is the area where we're going to be interested in, because we're only interested in the x values between 0 and root 10. So I'm going to go back and just going to show you what I'm going to do. I'm going to go to my table set, and I'm going to run this on the auto, and I'm only going to be interested in the values up to about 10. So that's up to about 4. So I'm going to come up here. I'm just going to say, let's start at 0. Let's move this up in increments of, I don't know, a half, 0.5. Okay, and we'll see what that looks like. So here we go. Okay, let's look at the table now. Okay, so why did I do that? Because that's going to give me a gauge as to where I'm going to peak out with that curve. That is, this is the area of interest in that curve right here in that range between 0 and that's going to be my root 10 value. Okay, so somewhere in there that peaks out. So I got to go to my calculator to see where that is going to peak out. So you can see that we're climbing in our x value and our y values here, but they kind of settle back down. So it looks like it goes to about 25. So that's what I'm going to do. I'm going to set up my my screen. So I'm going to define my window. Okay, I'm only interested in defining my window here. Let me get back to a slide. Defining my window between a 0 value of x and that root 10 value of x, which we'll just say is 4 is fine. You saw that the y values went up to about 25. I'm going to give myself some breathing room. I'll send that up to about 35 on the max value of y. Okay, I'm going to enter that. Okay, and then I'm going to ask for the picture. Okay, so see how I changed my, I used my table to find out where I'm going to peak out and why. So about 25 was where it was peaking out, but I'm giving myself a little breathing room saying y max up to 35. Take a look at the graph. Okay, Take a look at the graph now, and you'll see where it peaks out. Okay? You'll see it peaking out. Now, I want to know what is that value of x where that is maximized. So let's see. I'm going to go to F5. I'm going to go to the maximum right there. I'm going to have to skirt a little bit to the left over here. Okay. Enter that. Then I'm going to have to skirt a little bit to the right. Come over here. Enter there. Okay. And there I'm going to find where it peaks out is that the x is 1.825 and the maximum area produced is 2434. Okay, so 1.825 is my x max. X is equal to 1.825, and the area was somewhere in the area of 24, I believe. So let's go back to the sketch. Let's see if that proves to be the case. Okay, so I'm watching my my x value, which is FD here. Okay, I'm watching my area, and they should be in line with what I just figured out. Okay, my area is going to match. It's it's reached its highest point there, right? Okay, it's getting. It's just about 2434,185. I think that's pretty consistent with what we just saw here. Yeah, that's pretty consistent right there. My area max was, let's go back to the calculator and read that off again. That was at 2434. Okay, and that's pretty consistent with what I have here. And the FD, it might be a little bit off, some estimation errors, but that's pretty much consistent with what I found analytically. Now, of course, I didn't really find it analytically. I had to go to my calculator because the analytical solution will only be with the calculus, but I do expect you to use your calculator in these instances to find this optimal value, okay? And so there it is, okay? Everything all done with that example.